Hello, today I'm going to present about dress FID temporal regression of avatars with dynamic camera in 3D coordinates. This paper was published in CVPR 2023. So before I'm going to start a present about dress, I would like to talk about some background first. So first of all, we have SMPL, which is a deformable mass model with 68, 90 vertices to represent a 3D human body. So SMPL, it has two parameters, which are post parameters that uh, preserve the 23 relative rotation of joint with one global orientation and a 10 shape post parameter to characterize the different shapes of human body. And after that, we are having HMR, which is an end-to-end recovery of human shape and post estimation. This paper was published in CVPR 2018. So HMR is designed to minimize the reprojection loss of key point. It is considered of as the rejection human self and post estimation, which mainly depends on the SMPL parameter. So given the input image to a CNN-based encoder, this encoder encode the image feature and send it to the an iterative feedback rejection to produce the 3D parameter of SMPL parameter, SMPL model. And then the SMPL model output the 3D human mass as a goal to minimize the reprojection loss. This HMR model adopts the uh, discriminator to determine whether the given 3D human mass is from a real human body or not. By taking advantages of using the discriminator, it can be trained without using any 2D to 3D supervision. And then moving on, I am having a build, which is a molecular regression of multiple people in the deep. This paper was published in CVPR 2022. It is designed to infer the 3D mass of multiple humans in a single image from all age, within from an infant until the adults. So it can doing so by introducing additional but eye view repression to reason about the depth of human in an image. So Bill is trained and evaluate on a new created dataset which correlative human dataset that include the age level and the deep relation of the people in a single image. Here are the architecture of builds. So looking to the architecture, giving the input to the image with multiple people build output file maps. For the cost to find location, it used for maps of the front view and bird eye view, and then they expanded that four maps in terms of depth and height and combine it together to create a 3D center map and the 3D offset map. And for the cost detection, it extract the 3D position from the 3D center map. And for the find location, it extract the 3D offset vector from the 3D offset map at that extracted position. Combine these two vectors together, they can create a new 3D translation. And often 3D translation will be used with mass feature map together for the human mass parameter regression. By first, they take the parameter of the 3D translation and then embed it into the diff encoding. And then at the X and Y coordinate, they sample the feature map from the mass feature map and then add it to the diff encoding. And then they can produce a 3D post parameter of SMPR, SMPRA model to produce the human mass. And now I'm having a glamour. It is designed to recover the human mass in global coordinate from the video captured by the dynamics cameras. So glamour can do that by depend on two modules, which are generative motion infill and global trajectory predictor. So looking to the architecture of the lemma, we can see that it has 4 stages. For the first stage, it takes the input videos and then the MOT module gonna produce the 3D post parameter to the SMPL model, and the SMPL model output the more human body motion with occlusion. This question mark represent that the human body can be misdetected or go outside the camera frame. And at the second stage, it take the occluded body motion to the generative motion infiller with a job to auto recursively infill the missed human body to output a occlusion-free body motion. And this occlusion-free body motion are sent to the global trajectory, which this module is used to create a global trajectory of the input body motion depend on the local post parameter. So at the first stage, they take the global trajectory and then they try to refine it and optimize the camera motion to match with the input video evidence. So here are the challenge of tracking multiple people from the video captured by dynamic camera. First of all, the motion of the camera and the motion of human body are entangled. So it making it difficult for the model to learn about the trajectory of the human. And then the tracking of human through the long occlusion is difficult, such as the glamour, they fail to detect the server occlusion because of they consider only on the local human host without consider on the big cell like global coordinate. So to solve that challenge, Drex has come up with an idea of using 5D representation. So given an input video into Drex perform the inferring of 3D space identity and trajectory. The author of Drex has built or developed Trust with a 5D representation to recover 3D people along with the itineraries and trajectory in global coordinate. And then they also introduced a new data set which is called data kind for training and evaluation the trust to achieve the state-of-the-art results. Here are the architecture of trust. First of all, in the input video at the first frame, we can identify the number of subjects to be tracking. And then the whole architecture of track depend on two parallel backbone, which are image backbone and motion backbone. given the input image into this temporal feature extraction, it's gonna extract the temporal feature map, FI, and the motion map, OI. And then these individual brains perform their own task. First of all, the detection brain, they take the temporal picture map as an input, and then they try to detect the 3D position and the confidence of the human in that specific frame. And for the mass brain, they take the temporal feature map and the motion map together as an input, and then they're trying to output the SMPR parameter, which are theta and beta. And for the tracking branch, they take both of the feature map together as an input and estimate the 3D offset map. This map can identify the position change of people from previous frame to the current frame. And then a memory unit takes the 3D motion offset map and the 3D position together to create a identity and build a trajectory of human in a camera coordinate. Finally, the world map uh, estimate the world motion map. We can represent the 3D orientation and the translation offset in the global map from the 3D position and accumulate with the translation of that map. They can receive a global trajectory in global coordinates. For the Dynacam dataset, the author of Trace has come up with an idea to generate a new data set for the global human trajectory estimation. By first, they try to collect a variable video from previous data set as well as from the internet. And then they're trying to simulate the characteristic of video that captured by the dynamic cameras. So first of all, they're trying to simulate the 3D rotation of the video captured by the dynamic camera by projection the panoramic video captured by a static camera into a regular frame. And as a result, they can receive a videos that look like it is captured by the dynamic camera. And then they're trying to simulate the 3D rotation of the dynamic camera by using a regular video captured by a static camera. And then they apply the sliding window and then augmentation it to become a video that looks like it's captured by the dynamic camera that has the translation 3D. For the experiment, here are the data set that they use for training and evaluation. For training, they training it on 3D human post dataset as well as the 2D human post dataset and the newly created Dynacam camera. And for evaluation, they only evaluated on the multi-person benchmark and the Dynacam dataset. But for the Dynacam PD3W, it is the data set that they take 16 video from CVPR dataset that contains multiple, only two persons with a tracking annotation. Here are the evaluation metric that they use. For the global 3D trajectory estimation, they compute trajectory and velocity error. And for the multi object tracking, they report the ID switch, MOTA and IDF1 and higher order tracking accuracy. And for the 3D human pose and sub-estimation, they compute the MPJPE and PAMPJPE and the MVE errors. These are the table that's showing the result of dress. First of all, they estimate the global 3D trajectory with a two baseline, the first one is build and glamour. According to the results showing here, we can see that a dress can outperform the previous benchmark by in terms of global 3D trajectory. And for the 3D human pose and step estimation, dress can achieve a good accuracy in terms of PA and PJP compared to the previous measures. For multi-subject tracking, they also evaluate on two different data sets. The first one is the DINA 3D PW and the long occlusion MOPOTS3D. And as we can see, dress can outperform the previous measure in terms of multi-subject tracking estimation. So in conclusion, dress is a 5D representation that can represent a 3D mass identity and the global trajectory. And they can doing that by using two novel feature maps to represent motion of people across the time in the camera and the global coordinates. Thank you. That is all for my presentation today.
Any questions? No.
Since the recording is still on, should I end the recording?
Yeah, and then we start.
Really?